continue our next session, with our next session will be taken by Professor Amit Kumar Dotto sir on quantum communication, who is Associate Professor of GSNL School of Telecommunication, IIT Kharagpur. Dr. Sir, am I audible to you?
Yes, yes. Am I audible?
Okay. Yes, sir. Yes, sir. You are audible too. Yes, sir. It is our privilege to have Dr. Amit Kumar Dotto, sir. He is currently as an associate professor at GSNL School of Telecommunication, IIT Kharagpur. He earned his BE in Electronics and Telecommunication Engineering from IIEST Shibpur and PhD from IISc Bangalore. He joined IIT Kharagpur in 2018, and prior to this, he has worked in industry for almost 14 years as various roles starting from the design engineer to scientist. The industries include Texas Instrument, Broadcom Limited, NextP Semiconductor. He has been primarily engaged in hardware modem design for 2G, 3G, 4G, and Wi-Fi ultra-wideband system. He was involved in algorithm design to the ASIC design of the modem for various systems. At IIT Kharagpur, his key focus area in the quantum signal processing. It includes the development of quantum algorithm for parameter estimation in wireless communication and radar application. It also includes the development of efficient algorithm for quantum tomography, which is for state recovery. Another focus area in this direction is the development of post-quantum uh, cryptography, PQC, for enhanced security. He has also been engaged in research in wireless communication, FPGA implementation of various industry-sponsored wireless modem. Some of the work includes modem design of FMCW radar system, 5G modem, avionics modem for defense, etc. He has developed state-of-the-art lab for the FPGA-based modem development, starting from the algorithm to hardware. The specific research area includes 6G, terahertz, and petahertz communication, massive MIMO, beamforming, and management for millimeter wave, terahertz, including hardware architecture development. He has published almost 30 journals in IEEE Nature and has applied or granted 14 patents in India and US. He has guided 7 PhD students. Now, I would like to request Professor Amit Kumar Datta sir to start his session on quantum communication. After you, sir.
Okay, thank you. Give me a second. Just give me a second, okay?
Okay.
I'm just trying to set up some stuff in case it is required. Okay. Um, Thank you, everybody. Now I'm sharing my presentation. Right.
पक्का पता है ना?
Okay, so now let me see here. So is my screen visible to everybody? Am I audible and visible?
Yes, sir,
In
you
the
are
sense
audible. Your screen is visible, but not
my
the.
screen is visible?
Yes, sir. Yes, sir.
Okay, thank you.
But the PowerPoint is not visible. Now it is.
Yeah, yeah. Okay, so I'll be talking. Thank you. So I'll be talking quantum communication and the related signal processing aspect. But to be very frank, this particular one is, I mean, I will talk more about the quantum signal processing applied in the communication. So I loosely take it as talk of the quantum communication, but actually quantum communication is slightly different than what I perceive. So for me, it is more of a quantum signal processing applied for communications. Okay. So I'm, as Professor said, I'm Professor Amit Kumar Datta from IIT Kharagpur. So these are some of the topics which I'll be covering. So I'll be introducing what exactly the quantum signal processing and the communication is, and what is its recent role in the 6G and beyond, why people are so crazy about it. And then I'll be talking a lot of aspect of the system model. Why I'll be talking system model? Because that is something where you'll be understanding, well, this is the places where you can, where you can apply the quantums. And then I will be giving you some of the problem statements. I'll be discussing some of the problems. And I'll also discuss, like, is it so generic that you can apply just quantum and get the things done? So to be very, I just want to set the goal right. The quantum is not a magic wand. Okay, so it's not a magic. It's not at all. So it has to be used in a particular problems. Not all problem can, can be solved by the quantums. So I'll show you what type of problems can be solved and how they can be solved. So in this context, I will take you some of the practical works that we have done. So where quantum has been used, for example, RADCOM, which is the radar and communication systems, and in what context of the RADCOM this has been used, I will show you. Then there is a quantum Hamiltonian simulations, how it can be used, and what is the simulation problem, which you can use it for your normal problem statements. So in a brief, this particular talk will take you through the problems where quantum can be used, at the same time how you can use it. So which problem and how. So these are the two things which I will discuss in very thoroughly, with a lot of results that we have got it. I'll just start it that way. Okay. So these are some of the resources where you can find quantum related stuff. So if somebody is interested in quantums, I think people are more engrossed by AI. So I think, am I creating any troubles? Because it was getting some sound. It's fine, right, Professor? Oh, okay.
It is okay, sir. There is no.
Yeah, because
Actually,
some
there is a
noise.
surround sound from my side. There's a
Okay,
construction
that's
work
fine.
is going on. Okay. Let
No,
me.
no, that's fine. I was thinking that way. So it's, I know people are more engrossed by AI, ML and all. which is fine. But quantum is also a very undercurrent. So probably the next technological boom in the computer science and electronics is the quantum computation, not communication, computation. So which can be communication, quantum signal processing, and so on and so forth. Okay, so so probably this might be the right time for all the youngsters who really wants to start the quantums. Probably next 5 years down the line, things might be too developed, just like your AI and ML. So where things are only for applications. So this is the right time for entering into quantum domain. Okay, so if somebody wants to enter it, so this is the phase or the method, or rather, I will say the steps or the books or resources by which you can gradually build your quantum knowledge. So first, you read the first book, that is Quantum Mechanics by Griffith. So it's a physics book, but you don't have to read too many things. It's for the physics people, but from your electronics background or computer science background, you read the book at least few chapters, maybe 3 or 4 chapters, and then you start the things on from there. Then you read the Quantum Computation and Information by Chuang. It's a very classic book where the actual engineering aspect starts. The first book is for the physics, which you have to read it, and then you start into the computation, which is more on the more for the engineering perspectives. So there's a second book, and third book is also a similar line, where computation and info theory of the quantum comes into picture by M. Wild. And last but not but least, this fourth one is my website in IIT Kharagpur. So you can look at some of our works, which we have used it for quantum. Okay, so enough of the books part. So let me start it straight away. Why exactly or where you get really the quantum advantage? So you look at this figure. So this figure says that there is an H and there is a U. So when I say H meaning it's a Hermitian matrix. And when it is U meaning it's a unitary matrix. So what it says that if you have some sort of a system matrix, don't get into the word called Hamiltonian operator. So that's too much to understand, because for that you have to understand what is called a Schrödinger's equations. So I'm not getting into those things really. So this is not the this is not the time, or rather I should not start with the Schrödinger's equation. So don't get into the first lines, Hamiltonian operator and all these things. Okay. So you understand there is something called H and there is something called U. So what it means? So this is the fundamental part of the quantum. It says that if your system matrix somehow is a Hermitian matrix, there are many places where you can have Hermitian matrix as a system matrix. Okay. One such example could be, let's say, you take a data, a radar data rather. You have a lot of antennas. Let's say you have 10 antennas. You take all the 10 data of the antennas, and then you do a covariance of the matrix. So any covariance matrix is a Hermitian matrix. That's a very practical example. Okay, so there are many problem statements where you have a Hermitian matrix. There you can apply a quantum very much. Though we have in our research boundary, we have broken that concept as part of our research. We have shown that even if some system matrix is not Hermitian, but it has some structural similarity or structural advantage, you can use that and do the quantum. But the first thing is that to enter into a quantum, or to get into quantum, or to dream of quantum, your system matrix has to be a Hermitian matrix. That is the fundamental part. Okay. Once you have that, then you are into the quantum system. Then your classical computation of such system, whatever time it takes, whatever resource it takes, quantum can do it in a very, very, very fast, you can think of, or you can say it can be even a logarithmic scale. For example, if I have an n cross n Hermitian matrix, I want to do a inversion. So usually it takes O(n) cube, the complexity, right? But if I want to do it in the quantum, it can be in the polynomial order of log. That means O of log n polynomial, which is like a huge reduction, right? ON cube versus log of n. You can think of the reduction of complexity. So I'll try to explain some of the aspect on that. But this is where, as I said, that not each and every problem can be mapped to quantum. The first impression or the first thing that you have to think of is that you have to find a system which is basically a Hermitian matrix. If you have a Hermitian matrix, you can enter into, you can think of a quantum computation on that, or think of applying the quantum into it, and we'll see what is meant by quantum into it. Okay. Then I wrote a green box here. The green box is the unitary matrix. So which says that if you have a Hermitian matrix, there is a way to convert that to a unitary matrix. Now, this concept is coming from the Schrodinger's equation. So I think I'm not sure if how many of you are really aware of the Schrodinger's equation, wave equation. So what it says that a system will have, if there is a psi as a dynamics, so it can be a time varying dynamics can be equal to some h into that original dynamics. Okay, so that means so this is where your Hamiltonian or the Schrodinger's equations but come into picture. It says that del of del t of a psi is equal to h of psi. Now, what is psi? Psi is the probabilistic dynamics. So I will explain what exactly it is. So probably I will get into this one. So I always do that. Okay, so it is something like that. Say, for example, how do I define it? Put it this way. Let's say this is a place. It's a city, or maybe it's a room. Okay, so probably the room is a 14 cross 14 feet. Okay, and you as an individual are there. So there are certain chairs. Let's say these are the different chairs. 6 chairs up there. Let's assume. And this room is dark, and you can sit in any of the chairs. Now I'm here. Okay. Now you can be in any of the chairs, and you are not static. That means you are dynamic. That means you are sometimes you are here, sometimes sometimes you are here, after sometimes you are here. So you are here, after some time you are here, again you are here, again you are here, again you are here, and so on and so forth. It's all random, but time to time it's changing. So that means the condition is that your dynamics has 2 parts. One is a time dynamics, and there is a space dynamics, which is very practical, right? You can think of any such any physical problems which has this dynamics. I mean, we as individuals have the same problem, right? When you are in a college, currently you do not have any dynamics because you are sitting in a chair. But apart from that, you think of your whole day in the college. So you enter into the college, then you really don't know in the next 3 hours where you will be, right? So you'll be changing one place to another. So after maybe 10 minutes, you go to one class, you take a class or attend a class, come back from the class, and you do not know where you may go. You may go to cafeteria, sit there for 10 minutes. Again, you may go to probably any other places, sit there for half an hour. So what I'm saying is that every element, it may be you, it may be a particle, it may be a photon, it may be a universe, or it may be the whole sun or whatever, anything, anybody has 2 dynamics in the real system, and both are probabilistic. Why it is probabilistic? Because you really can't predict after 10 minutes where you will be, right? Suppose you are here, you are taking a class here, and after taking the class, you somehow going to the cafeteria. Okay, and you do not know how long you'll be here in the cafeteria. After your cafeteria is over, you go to one of your colleagues' room and do a chit chat for another half an hour, and then and so on and so forth, right? So this time and your space of your your dynamics, that means there is a position and there is a time. So your position and at a particular time itself is probabilistic. Can I think of it that way? So I can say that I can define a probability x over time. Okay, so that means it's the probability of your position, which is a time variant. So I should put it this way. This is the right way to define. So that means you have some dynamics probability. Probability of what? Probability of probability of you being in a particular position. Okay, so that's time varying. Okay, so that is what is called a time space dynamics of a particular object. So which the object could be a proton, it can be electron, it can be an atom, it can be a human being, it can be a car, it can be anything. You think of any damn thing in the world has these two dynamics. So it is probabilistically varying its space, and from time to time it changes the space. This is which is very natural for us. You think of any animal also, a particular animal, if you look at a jungle, it will be there in a particular place, but after some time it can roam in another place. After some time again it moves to another place. So that means probabilistic. So you cannot predict where that particular animal will be after 1 hour or 2 hours, right? This is where the probability comes. So that means I can always define a probability of a particular object in a particular space, but that doesn't define the whole thing. I cannot say what is the probability of a dog. What is the probability of the dog being in a particular park? I can't say that. I can say what is the probability of the dog being in the particular park at time 10 a.m. That makes sense, because I do not know whether at 10 a.m. he will be in the park, or at 3 p.m. it will be in the park. I have no idea. So there is always a time associated with any object regarding the space. I think I make the points very clear. So this is what exactly called a time space dynamic of any object. Okay, root over of that. So root over of this particular quantity P, which is this quantity, is what your psi is. Understood? So what exactly is xi mean? Xi is the root over of this probability. So this is called a Schrodinger's wave equation. So it is not a wave equation. This is the probabilistic root over of that quantity. It's a quantity whose root over is what the xi is. Now, where the Schrodinger's come into picture, Schrodinger's is basically trying to define this dynamics. Okay, what is that one? This is precisely this dynamics. That del delta xi is equal to h of psi. So what it means, that means this xi isn't moving in a Brownian motion. So if this xi is very random in nature, what is meant by random? It says that if the object is moving in very random, then I cannot define this pxt. For example, what can I say? A mad person, he just roam around here and there. I'm not talking of that dynamics. So that's called a Brownian motion, right? So if I have some sort of a room here and there is a wild animals, so it will just move here and there all the time. So this is also a time space dynamics, but I can't define such dynamics. Why? Because it is too random in nature. There is no predictability inside it. Absolutely difficult to predict if the object is here after 1 second where it will be. Okay, so this kind of dynamics I'm not talking. So it is basically I'm talking of those dynamics where it is slightly predictable, in the sense that it is not a wild motion kind of thing. Okay, it is slightly controlled motions in that sense. So that means I have a house here or a room here. Just the example I give you, you are entering into college. This is your classroom. This will be your cafeteria. This will be your colleague's room. This will be your head's room. This is other rooms. So you enter here, be here for 1 hour. After some time you may be here. After some time you may be here. After some time you may be here, again here, again here. And so you see that this is also not predictable. But this is more of a discretely your position. So you may be here, not anywhere else. And it is also dynamics, of course. This is also not predictable. Okay, from here where I'll go, I don't know. But it is not a very continuous way of movement. Okay, it's a very discrete way of movement. I will be here. After some time, I'll be standing here. After some time, I should be standing there. So this sort of probabilistic notion, what I'm talking is Schrödinger's equation. So when say Schrödinger came up with the definitions of this dynamics, what he meant to say is that such kind of dynamics, that the object goes to a particular positions from time to time, but you have no idea when it goes. That's precisely what I'm going to say is here. Okay, and all our practical objects actually behave in that way. So nobody goes in a wild motions. Okay, everybody goes in the in a very disciplined manner, but it will be dynamic. Positions are fixed, but you go here and there, because you take your example in the whole college, you just simply don't spend your time 1 hour in the corridor, right? You always go to a particular room and spend your time. So that's, I mean, we all do that, right? When we go from, we either spend time at home or a cafeteria or hotel or a restaurant, some colleagues rooms, so on and so forth. So that means our spaces are fixed, but somebody can't predict where I am at a particular time. So this is what I'm saying. Okay, so when you have this kind of physical dynamics, so I define a probability of what? Probability of that object at a particular x. That means what is the probability that this object will be in this space? I can define that way. So that's the probability of x. But you see, that's a time function also. This is why it is, because at a particular time it can again move to another place. So it is something like that. What is the probability that you will be in a cafeteria at 10 a.m.? If I have that kind of question to you, so it's a probability of a space, but it's a time value. So this is precisely what I'm saying as a P probability. Now root over of that is called a Schrödinger's function. So this is psi. Now Schrödinger's equation is that if you have this kind of function or follows this kind of principle, most of the practical objects, physical objects follow this, then you also follow Schrödinger's equation. That is precisely what your Schrödinger's equation. So I'm taking little time because without it, things won't move out. Okay, so that is precisely what it is. So del t of this psi is equal to h into this psi. Okay. This is what it is. So it says that if I have this dynamics, then the time varying function of that, the partial derivative of that function is equal to some h, which will define it, because that is the whole quantum aspect of that. So h is equal to h into the psi. So now this is exactly what your Schrödinger. So this h is also known as the Hamiltonian. So if you look at the word I have used, it's called Hamiltonian operator or Hamiltonian. So now from a physics people point of view, it's an operator, but from a signal processing person or a communication person, it is nothing but a matrix. Okay, so now before I get into the actual presentation, probably I will spend another 5 minutes to set the ball. I could not put it in the presentation because that won't describe so many things. Okay, so now this is the partial differential equation. Okay, now this partial differential equation has a very interesting solution. Because in the partial differential equation, it has an interesting solution. It says that this psi, which is a function of x and t, it's a summation of ci e to the power minus I should not say psi and some function of t, psi t. Okay, so this is how there will be some more stuff here, but this is a solution of it. Okay, so this is solution of this partial, what I should say, differential equation. Because now I'm getting into the mathematics. So now we'll connect that how this has anything to do with the quantum communication or quantum signal processing. What is the strength of this equation? So what exactly it means? Okay, what it means is the following. So what is this psi I? Psi I is the eigenvalue of this matrix. Okay, so what I say. So this psi I are the eigenvalues. Of what? Of H. Now, from a physics point of view, that H is an operator. From our point of view, this is a matrix. So what exactly it means? It means that this xi is equal to C into I to the power so and so, and this is the eigenvalue. That means if this H is an n cross n matrix, so this summation will be only for n. Now, in another way, I view it. Other way, from a communication, this is the physics people understand that. But when you actually get into the engineering point, this is where our strength is. So it means that this one, we think of it as a vector. Vector, you understand what is called a vector, right? It's like a vector, meaning what? Vector is nothing but some stack of elements. So that's a vector. Okay. So it's a vector. So this vector is a Ci into another vector who are orthogonal in nature. Okay. So it means that I have coming from physics to the engineering, and then I say that, well, this xi is actually a vector for me, which is a summation of many other vectors. Now, who are these vectors? These vectors are orthogonal in nature. Because it is orthogonal in nature, then I can say that this is nothing but a linear combinations of these orthogonal vectors, which creates this vector xi. Okay. So now that creates a very interesting problem statement for us. So there are two things that we are taking out. First of all, this psi, whatever we are talking of, these are all eigenvalues. Now, if you look at the solution, this guy, this is e to the power something, right? Now, from an engineering point of view, what is e to the power? In e to the power, what is basically is nothing but unitary. Okay, so which means that this psi or this e to the power function is nothing but some unitary representation or unitary function, because unitary star into unitary is I. And this is the same thing for exponential also. Exponential multiplied by its conjugate is also 1, right? So which means that I have some similarity point from the quantum to that. So what it means that if I have an operator or a system matrix which is Hermitian in nature, and then I can find the eigenvalue of this matrix, then actually I'm done. So what it means that if I can have a system matrix which is Hermitian in nature, then if I can find out the eigenvalue of this problem, that gives me a lot of things in the quantum communication or quantum things. So that is the fundamental part of Schrodinger's equations. Schrodinger's is physics, but when I take it, I don't look at this equation, rather I look at this equation. And who are these C? C are basically the probability functions. So what it means that if I have a room and I have boxes where I can only go, okay, so let's say I have 4 boxes, so I can always say what's the probability of me, what is the probability that I'm in box number 1. So I can define it like a p1 of the function, obviously, right, because that varies from time to time. What is the probability that I'm in box number 2? That's a p of 2. What's the probability that I'm in box number 3? That's p3 and p4. Okay, so these are all probabilities, because all my psi are nothing but this root of all of them, right? So this C, basically whatever the C I'm talking of, the C1 square, the C1 square is nothing but P1. C2 square is nothing but this P2, and so on and so forth. So which means that I have a vector which is broken. So these are all orthogonal, that means they are all basis vectors. So I can say that this vector is a linear combination of a lot of basis vector, but their coefficients are all probabilistic values. Probability value represent probability value. What does it mean? It means that all the summations of individual C1s will be always 1. So in a sense, I can say that, in a sense, what I can say, I have a xi which can be expressed as like this. If I just have two values or two quantum values or two these guys, this orthogonal basis, I can express it like that. So that means my system matrix is simply a 2 cross 2 Hermitian matrix. Hermitian matrix. So if I have a 2 cross 2 Hermitian matrix, it has two eigenvalues. So these two eigenvalues, if I stack them, I get one variable, and that can be broken like that, because this is precisely what is meant by this equation. So, and the condition is that alpha 1 square plus alpha 2 square should be always 1. So that means individual alpha 1 and alpha 2 square are basically representing what is the probability that I am in this box. What is the probability that I'm in this box? So 0 and 1 are basically, you can think of it's a basis vector, or you can think of it's like a box. So the whole thing is like a vector space, right? So it's like I have two orthogonal bases, their linear combination is creating a vector. So this is basically a vector space for me. So underlying mathematics is that as many as bases are there, that is representing a particular Hermitian matrix. For example, if I have this guy, say for example, I have another xi, which is equal to alpha 1, let's say a1 plus alpha 2 a2 plus alpha 3 a3 plus alpha 4 a4. Okay, what does it mean? It means that this is a 4 cross 4 Hermitian matrix is getting represented. So there are 4 eigenvalues, and each one of them is representing the eigenvalue part. Okay, so what it means that, so it has a room. There are 4 boxes in the room. So this alpha 1 square represent the probability of the component to be in the box number 1. Alpha 4 represents alpha square, basically. Alpha square represents the probability of that particular element to be in the box number 4. Okay, so this is precisely how I define it. So which means that when I'm trying to define the dynamics of I have to define it using all this probability mix up. Otherwise, I cannot define. I cannot say your probability is just alpha 1 square. That's wrong, because your probability is alpha 1 square to be in the box number 1. So this is the complete way of specifying your space and time dynamics. Okay, so that is one part of the story. Second part is that yeah, so this is how I represent my quantum state. So this is basically somehow representing a 4 cross 4 Hermitian matrix, and each one of them represents the probability of this particular element for which these dynamics come in the eigenvalue state 1. So space meaning it is eigenvalue. So when I say I am in a box, 4 boxes are there. So these boxes are basically called the 4 eigenvalues of this. So when I say I'm in here, alpha 1 square, what does the alpha 1 square meaning? That means this object has a probability of alpha 1 square to be in the eigenvalue state 1. Alpha 3 square meaning it is the probability that this particular element will be in the eigenvalue state 3 with probability alpha square. So that's precisely how I define that. And every A1, A2, A3, A4 are orthogonal in nature. So it's basically, you can think of, they're all bases, and that is creating this particular dynamics or this vector. So this vector is generated by, so you can see that I drifted from physics completely. Physics started with all the Schrödinger's equation, but to me, what I finally come up is that I have a simple vector, and I break the vector into 4 to as many as component, and each and every component is orthogonal in nature, and their coefficients are probability component. So it is a linear combinations of orthogonal vectors I'm creating another vector. That's all. So there is nothing called physics now. So all this probability bagara all are gone now. So it is a vector which is a linear combination of several orthogonal vectors, which is anyway any vector is like that. If you pick up any vector from a vector space, so it is that. And but the only difference here is that from a traditional vector space is that it's also a vector space. The only difference is that the coefficients strictly has to follow this alpha I square has to be. Okay, so which means that they strictly represent the probability, unlike a normal vector space. So this is what the things here. So now what is the advantage of this concept? Why people are talking up so much here? So the reason why it is so important here is that if I'm considered a binary, let's say I'm considering a simple binary system, what it has 0 and 1, right? So it can be either 1 or it can be either in 0, not both of them. Okay, because you observe something and you get only 0 and 1. So it can be either 1 or it can be either 0. But the advantage of quantum is that when I say it's binary quantum system, so I don't define it just like a discrete 0, discrete 1. I define it like this. System dynamics will be in alpha with probability beta 1. So what it means? It means that that particular system will be in 0 eigenvalue state with probability alpha square and B1 with probability beta square. So I use the term and. So which means that it has both the state existing, unlike your normal binary. So when it is a binary, it is 0 or 1, not both of them. Obviously, right? Suppose you have a gate and I have logic 0, logic 0. So what's the output here? 0. Very predictable one, right? But if it is quantum, it's not that. I can't say, suppose it's a, though there is nothing called AND gate in quantum, let's say some hypothetical quantum here. Here, I can't say whether it's a 0 or 1. It can be both, either 0 or it can be both, either 1. So now you look at the strength of this element. So you can say, oh, it's a confusion because it can be either 0 and 1. So how do I determine a particular state? We'll come to that because that is not the issue, determining the particular state. Because when you measure it, it will be one of them. But at a particular time, it can be either here or either here, both. Because it is everything, that means both are there. So its information or capability actually more. So which means that if you go with 100 rupees to market, you can buy anything which is 100 rupees, just one. Suppose I tell you, okay, I give you another 100 rupees. So what you can do? You can either buy two stuffs, or you can buy just one and give 100 rupees, or you can buy another stuff which is worth 200 rupees. So my point here is that when you have 100 and 100, you have the luxury to choose both. Either you can buy one stuff of 100 rupees, another stuff of 100 rupees. Okay, but if I just give you 100 rupees, you can buy only one of them. If I add another 100, so you can buy actually one, you can buy two, you can buy three of 100 rupees each. Okay, so that is like, if I give you more and more things together, you have more power to purchase, right? This is precisely what the quantum strength is. So quantum strength is that parallelly it has 0, it has 1, both sitting at the same pace or same time. Okay, because probabilistically you do not know whether you are in 0 and 1, but both has the probability. You can't say it has only just 0, nothing else is there. Where if you have a, suppose it's a NOT gate and I give a 0 here, you can predictably say it is always 1. But if it is a quantum NOT gate, there is a quantum NOT gate also come there. If I give a 0, you can't say this should be 1. It has 0, it has 1, both. Okay. Both can be present there. So that means that a quantum will have all the states together, and then you choose whichever you need. So look at the strength of the quantum. That is why quantum becoming so powerful, because it allows you to have all the states together, but probabilistic mixture. It's a probabilistic mixture. That means 0 also exists, 1 also exists, and both. So it's very difficult to imagine in a normal sense, but that's how it is. So the circuits today, there are circuits coming which will ensure that both come into picture. So it is not like a digital logic where the output is very predictable. So quantum meaning output has both of them. Now the question is that doesn't it get confusion because I have both? Then which one to choose? How do I then proceed? So that is a different story. So then you can tweak. So that means I want more and more zero. So I increase this alpha somehow, or I want more and more one. I increase this beta. So your quantum communication or quantum computation is all about this game. The game is, if I want specific thing, I just try to increase the probability there so that I can have more and more that value and the other value will be less. Okay, but I have the choice. That is my point. I have the choice to get 0. I have the choice to get 1 from the same system. But had it been a digital, I have no other choice. Just one of them will appear. Okay, so that's the strength. Because it has all of them together, it's so powerful. It's so powerful than any imagine. So that means I have the complete two things together, just one instead of one thing. Okay, so that is where the quantum strength comes into picture. Okay, so now I'll be a little faster. Okay, so don't worry about all this. So this is basically a point where a computation, how fast a computation can be done. So I have a pictorial view here. Let me see. Yeah, so this pictorial view. So this is a very powerful pictorial view of what I wanted to say. So this is a simple digital serial computations where I have one lock. Okay. And if I want to do many things together, I have to put multiple such locks. Okay? But when it comes to the quantum, it's actually all merged, you see. So there is a difference between the two figures. So this figure and this figure, you see, because this figure says that I have everything available at the same plate. This thing says that yes, I have everything available, but they are all segregated. So which means that I need more computational engine, because I have one engine here and there are multiple such engines. But this guy says, quantum says that no, you don't need multiple such engines, because within the same engine I have all of them things available here compared to any serial one. So this is the part of the quantum. Okay, so that means I have a serial computing system which unlocks things one at a time. If I want to increase the parallelism, I have to just replicate the whole stuff there multiple times, which increases the resources. Probably it decreases the time, but when you come to the quantum, it not only decreases the time because it is also doing the parallel stuff, but it resource requirement is too low, because you need n such parallel combinations or computational units, whereas when you come to the quantum, the same parallel things can happen using one step. Why it is one step? Why same thing can do all the things together? That means it has all things in it. Then only I can do it, right? And that is defined by this one, this concept, because the quantum system has both states. If it is just a binary system, it can be more than binary. Both of them together, I have both of them. That means I can process 0 1 both together. Now you tell me what you need. That's all it is. Okay, if I need more 0, I give you the 0. If you want 1, I give you the 1. See, so you have both the choices. So this is precisely what the quantum things does. So this particular figure tells everything what I want to say here. So basically, when you say quantum, it is a parallel computation. That is why it is so powerful. Why it is parallel? Because I can process 0 1 both together. That is why it is parallel. Okay, but it need not separate resources. It can be the same resources which can do the things at the same time. Whereas if I want to do same task using the classical stuff, I need multiple such units. Suppose I want to process the 0, I want to process the 1, I require both the units. Okay, but if I want to process all of them together in one unit, that's precisely what it does. Okay, so this is a very powerful figure which I wanted to say. Okay, now so this is a very interesting stuff which I just discussed it. So basically, so at the end of the day, what I need is a Hamiltonian system. That means any system having a Hermitian, any systems. I'll give you some of the examples where I said, yes, that system is Hermitian, then I can do the processing. This unitary, why I wrote the unitary, that is because I want to do the computation. So the quantum gates, like for example, in digital, you have gates, right? You have AND gate, NAND gate, OR gate, NOT gate, whatever, XOR gate. Quantum also, there are certain gates. So they are not AND gate or gate. They are called Pauli gates. Okay, so these are Pauli gates, whatever I have written. So this is the truth table you can think of. Okay, if you don't have to remember, you can always do a Google and see what are the different quantum gates. So I have written few of them, like Pauli X, Y, Z. There are many. There are many other quantum gates available there, like Toffoli gates and NOT gate, quantum NOT gate. All these things are there. So I'm just, and this is the truth table. So now when you say truth table in quantum, there is nothing called truth table or anything like that. So everything is a matrix. So in fact, a gate, when I say gate, that is also a matrix. So this is the kind of odd way of expression. For example, if it is an AND gate, it has a truth table. Y is equal to AB, A plus A into B, and A, B, you write it somewhere, and then Y, there is a truth table comes, right? But when it is a quantum, the gates are different. The notion of gates are different. So the gates are basically called Pauli, and you can say the equivalence of truth table is a matrix. Okay, so which means that this is the basic gates, which is the 2 cross 2 gates. These are different gates that is available, and there are many such gates. I've just given a few examples. And this is like a, as I said, this is a state, xi is equal to alpha 0, beta 1. So as I said, so this represents that the quantum state can be in 0 and 1 both together simultaneously. And the probability of its being in 0 is alpha square, and probability of its being in 1 is beta square. So alpha and beta are not normal coefficient, it's a probabilistic coefficient. So which means that this particular xi, which is the output of something, it represents, says that I am in both the state. Okay, to draw an analogy, I can tell you this way. So if it is a simple, if it is a simple binary, I would say this xi would have been just 0, or it is just 1. Okay, that means this xi is either 0 or 1, not both. But when it is quantum, the same xi is this. So that means if I have some sort of a gate, if it is classical, it can be just 0 or 1, not both. But if it is quantum, it is 0 and 1 both together with this equation. This is what it means. Okay, this is precisely what it says. Okay. Okay, so as I said, there are different gates available. Pauli's are the first basic level of gates, and this is another gate called NOT gate. So this is also a reverse gate. It's not a NOT gate. It's also actually a NOT gate because it is just doing a reverse. This is a control NOT gate. I'll not get into the too much details of it because that is not the intention of it. We will not be following what I say. Just understand that there's something called a gate. Okay, so now where exactly it fits? Okay, so where the quantum technology fits in the current context. So there are 3 branches of the quantum. One is called communication, quantum security, and computing. Okay, so there are 3 branches. And left side and right side, I have written some of the topics of 6G and 5G. So these topics, some of the topics are all having this communication, security, and computing concept. And this whole thing, this three bucket, can all be well done in quantum, like quantum traditional communication to quantum communication, traditional security, quantum security, traditional computing to quantum computing. Okay. Apart from that, it has something called crypto, which is quantum crypto, that is more for the security perspective. So this is the basic way of understanding how a 6G component can fit into the quantum domain. So you can see that everybody actually goes into this, whether it's a V2X, UTX, ADAS, MLDL, blockchain, terahertz, no matter what it is, all can all can go to communication, all has a security, all has a computing aspects. Okay, and all three buckets, all these three buckets can be well done in quantum. I'll show you some of the examples so that you can actually get a feel of it. Okay. This is another practical example where it shows where exactly the quantum will be used in next 6G. So this is a typical, typical 5G base station concept where you have remote radio head. So multiple such remote radio head will be there in 6G, and they are all linked with fibers with a BB unit. That's the baseband unit. Okay, so so what happens is that all your computation, in fact, really happens in BBU units. And this is where this BB unit will send the data to mobile phone. This is a typical 5G infrastructure, right? So when you talk from a mobile, it will be connected to one of the RRH. So it's not called a base station. Typically, it's not a base station anymore. It's RRH, remote radio head. So it will be part of the base station. So you can have multiple such RRH for one single base stations. Okay. So you connect via a mobile, you connect to one of the RRH, and this RRH will simply take the data and do a digital conversion, just make it one on-off key, and then send it through fiber to the BB unit. So actual computations of the base station side will be happening in the BB unit. And after computing, all your protocol stacks will be running here, and then it will send the data to the mobile core, that is called a core networks. Now this BBU unit, which is currently a lot of servers are there, right? So if you go to any of these BBU unit stations, I don't know in your area which is the nearest BBU stations, but usually maybe 5-kilometer radius, if I take it, at least one BBU station will be there. So you can, if you have the chance, you can go and see there are a lot of racks there, a lot of racks of servers there. So this exactly where the quantum will be replacing. So in near future, maybe 10 years, 15 years, 20 years down the line, all will be quantum machines, because this is the computationally intensive activities going on. Okay, code also will be slightly reduced, but core I'm not very I'm not very sure how core can be replaced by the quantum, because cores are typically the switches, and switches are not heavy computational things. So switches can be, depends how big the switches are, but the BB units are really big units. Okay, so that is the future where it can be replaced by the quantum part. Okay, so this is more mathematical part now. So I'm trying to explain how and where the quantum differences come. So I take a very simple example, and I'll show you that this simple example, what it means in terms of the classical, what it means in terms of the quantum. So let's take a very simple data model, y is equal to hx plus w. So what is this model? That's a antenna out, receive antenna model. So you send a signal, you receive the signal y, and that's sorry. So there is so you try to send x, so it's multiplied by the channel h, and then there is a noise addition at the receiver. So y is what your received signal at the y. So this is a simple data model. Okay, so it's a single antenna, single time data model. Okay, so now, so how do I define a detection data? Suppose I want to detect x from this data model. So I know h because I have estimated h, and then noise, I don't know anything. It's a simple classical problem, right? Data detection problem. If some of you are from communication background, this is a one of the classical problems. Okay, so you can do a maximum likelihood detection. So what is the maximum likelihood detections? So x cap is this, you are trying to minimize y minus x mod square and try to find out what the value of x such that this quantity is getting minimized. Okay, so this is a typical typical classical data detection. Now how do I represent it in a quantum system? So the same problem, the problem number 4 is now, so this is the classical problem. So classical problem meaning this is exactly what I want to do. So x cap is I want to find out that x cap for which this data is minimized. Now okay, so now this is my quantum signal representation. So let's see what it means by the quantum signal, because what it says that I have another before I get into that, this is I want to know that to tell you. Okay, probably I will come back to that later. So what I do here is that I want to represent this signal x cap to a quantum data. So this is a classical data, and if I want to process something, your actual world is still classical. Suppose I send a signal to the world and that data is still classical. There is no, there is nothing quantum there. It's the processing which will be kind of quantum, right? So your signal is still classical. What you receive is classical. So when you come to the quantum domain, you have to first convert that signal to a quantum signal. Okay, so what do I do? It's a very simple technique. Technique is that, see, look, this is y minus x mod square, right? And you are doing basically a search at the end of the day. Okay, so at the end of the day, you are doing a simple search operation. So what I can think of it is that this x cap. Okay, so let me put it this way. Let me just explain it a little more than what I need to say here. So you have this y minus x mod square, right? This is so you want to find out that value of x which minimizes that. And what is x? X can be many such values of x. Why? Because it may be a constellation. So let's say it is from 256 QAM constellation. So how many possibilities of x are there? That's almost 256 possibility. So what do you do? In fact, in classical, so you can say that, well, you put each and every value of x into this equation. Let's say this is z, and for every x you compute the value of z, right? So how many z you will get? You will get z1 to z, if it is 256 from 256. Why? For each and every value of x which is corresponding to 256 QAM, you calculate this value, right? 256 values, you get it. Then what you do? Then you do a search, right? So as I said, the problem was minimize this quantity and you find out that x which minimize this quantity. That means what value of x out of the 256 that minimize this quantity. That means you have 256 value of z possible and you search which one is the minimum value. So it's a very classical problem, right? So that means you are getting 256 values and you are trying to find out what is the minimum value. That is a very, you can write a C code and find out. That's a classical problem. But you see, you can think of the complexity of the problem. Okay, so the complexity is O(n) square and more than that, or O(n) cube also. But if it is quantum, so first what I need to do is that I need to represent this in quantum. So what I can think, instead of viewing this whole thing as discrete 256, quantum views that as a combinational things. So what does it mean? It means that I define a quantum signal. So you can see that one of them will be the minimum value, right? Let's say Z5 is the minimum. That means the fifth constellation in QAM 256 coin is the one which minimizes the value. So this is the guy which is the minimum value, right? So what I do, first I normalize them. Okay, normalize in such a way that all the mod of Jedi square is equal to 1. I can do that. How can I do? I take the sorry, I take the mod square of all of them. Okay, so that means I take all of them and divide it root over of that value. So it's a simple technique. Okay, I don't have to do any search. So I normalize it such that their individual element square is equal to 1. Then what I do, I take a very simple approach. Then I define that, well, I have a psi or a quantum signal which is equal to this Z1. This is just a notional thing. 0 meaning it is just a orthogonal space plus Z2 dot Z256. 256. This is just a notional thing. Don't worry about this 0, 1 and that can be anything. Okay, these are all vectors which are orthogonal in nature. Now you see that instead of thinking as a set of 256 different value, I combine them together, or I can imagine that whole thing is something like that. Understood? So that means I imagine that they are nothing but a coefficient. I normalize it such that their mod summations is all equal to 1. Then I simply define a xi where my coefficients are like that. Then what am I getting? I am defining a xi which contains everybody together. That means all things are there with me in one single vector. One single vector represents everything. And obviously there are techniques, so that I'm not explaining. How do I find out the Z5, which is the minimum value? That's a different technique. Okay. But at least I have the representation. So this is one such technique by which I can convert my signal, classical signal, to a quantum signal. So there are many techniques. So it all depends on the problem. So in this case, what was the problem? Problem was a search problem. Okay. So this is basically a search problem. So I need to find out the value of X, which can come from maybe 256 or 1024 constellation points. So I need to evaluate 1024 times or 256 times and find the list of that. Okay. So that's a search problem. So when I say I want to convert this problem to a quantum, so what I do is that I just take these values evaluated at each and every point, normalize it, and then completely represent a quantum state, where the individual, these coefficients are those evaluated y minus xi, those values. So what does it mean? So that means now I have this guy which contains all of the value of those coefficients together in one single vector. I don't have to go to individual, this is what, unlike this guy, where it's a set. I have to now, instead of searching, so it's a set which contains all 256 discretely, right? It's a set, it has 256 elements. Rather, I say, no, in quantum, I can convert that to a quantum vector where coefficients are all these values and it's one value. That means one vector having 256 entries, rather a set having 256 values. So you see the terminology change. It's a set in classical having 256 discrete different value. In quantum, I just convert it to a single vector having just one value, but all of them are merged there. Merged meaning they are all separated. This Z1, Z2, Z3. If I just add them, it will not work. They will just mess up. So I add it through a orthogonal vector. So they will not mess up. Obviously, right? If I add A plus B, it will just kill everything. But if I say I add A into sine omega t plus B into cos omega t, am I messing up? No. I'm not killing A and B, but I'm still adding A and B together. So this sine and cosine are actually orthogonal. So that means when I want to add multiple values and I still don't want to kill them, I have to just associate a orthogonal function with all of them and just add them. Obviously, that we have all learned it. All your Fourier series and Fourier transformations all represent the similar principle. So they're all basis vectors. So that means if I have orthogonal functions, just multiply with the coefficient or those values, and then you add them as many as you add. So if I want to add 5 such values, find 5 such orthogonal values. This is precisely what I've done. Okay, so now what is the value here? This is just one single value, but within it, these two values are perfectly sitting together, and I can reconstruct A and B perfectly fine. But had I not given sine and cosine, what would have happened? Then I cannot reconstruct A and B. So this is precisely the quantum does. So I take all these 256 values separately and then associate a orthogonal function, which is the quantum's job, and then add them, and I get one vector which never interferes. Z1 doesn't destroy Z2, Z2 doesn't destroy Z5. But beautiful part is that in one single vector, all of them are sitting together. So this is what the quantum gentleman is doing. Okay, so now I move on. So this is just one way of representing, a problem. So this is one problem where this is one way of representing this vector to a particular quantum. So now this is called a amplitude encoding. That means I have multiple such values, just put them together, normalize them, of course, and add them along with orthogonal function. That's precisely what the quantum is. Okay. The beautiful part is that all of them have all of the values. So whatever resultant function you get it, they have all the values and all separated. Okay, so next one is this is where I want to show you. Okay, so where you want to do data processing. So this is a typical classical data processing principle. So it could be it's a linear, of course. I'm taking linear. So how I differentiate between classical and quantum. So where the difference lies. Okay, so let's say I have an observation vector y, and I want to develop some sort of a precoder. I think you might be knowing what is precoder, or equalizer also. Mostly it is equalizer, not a precoder. So if I have an equalizer, I multiply with the W and I get back that x. Okay. So for example, if I want to do LMMSE or MMSE estimations, I want to estimate x. So what I do is that I have a vector y, then I multiply with a W matrix, and I get back the internal data which I want to know. So these are typical equalizers. So this W can be a matrix, precoder equalizer. It's a classical way of data processing. But when I want to do a quantum way of data processing, a very similar approach happens. It is also a vector, matrix, and all these things. But there, this W will be changed to either U matrix or H matrix. Okay, so as I said here, either it is H, that is fundamental. So either it can be a Hermitian matrix, which is okay, but Hermitian cannot be processed directly. That it have to convert it to unitary matrix, because that's how quantum gates are associated with. But there is a way to do that's called Hamiltonian operation. So if I have an H, I can get a U, but you have to get an H. So if your system matrix, this W is somehow a Hermitian matrix, I convert that Hermitian matrix to a unitary matrix and process it as a quantum operation. That means this finding out U and all these things becomes very easy in quantum. Okay, so this is the fundamental difference between classical and quantum. So, classical, your system matrix or the matrix you would like to develop, it can be any matrix, but in quantum, this W cannot be any matrix. It has to be a Hermitian matrix or a unitary matrix. To be very frank, it should be unitary, need not be a Hermitian. But even if it is Hermitian, that's fine. I can convert it to unitary. But if it is some other matrix, okay, then I can't do anything in the quantum. Okay, so that is precisely what I want to say here. Because if it is a unitary matrix, I can represent this unitary matrix in quantum gates, like whatever I said, like Pauli gates. These are the fundamental gates. Okay, in quantum. So I can represent this U matrix very easily using Pauli gates or its fundamental gates. Otherwise, I cannot do that. Okay, so that's the difference between quantum and typical. Now, it is your job is to convert this W to some sort of a Hermitian, sometimes possible, sometimes not possible. At the same time, that also puts a limit, which problem you can take it to the quantum, which problem you cannot take it to the quantum. So you should have some sort of a hawk's eye to find out where I can find a Hermitian matrix. Okay. Okay, so this is a typical system diagram which is practically used here nowadays or being proposed, where you have a classical data, then you have a classical to quantum conversion. I just showed you one example, amplitude data. So that means you have a classical data that has to be first converted to a quantum data. Quantum meaning that I just showed you one of the example. Then you can do quantum signal processing. Then you have to do a reverse process, quantum to classical conversion, and then again you can apply some classical disk if you want, and then transmit to the through the antenna. So this is the typical mode of future of transmitter receivers. Okay, and again at the receiver side also you receive a data through antenna. That's a classical data, electrical data that has to be converted to a quantum data, which I gave you one example using that amplitude encoding. Then you do all your all your quantum. Once you get the quantum, then you process the everything in quantum, but provided your system matrix is either Hermitian or unitary. If it is Hermitian, fine, or unitary, fine, not anything else. Okay, so you can do parameter estimation, signal detection, channel decoding, everything. So we have works here heavily, and then again you reconvert back to the quantum to classical conversion and use it for practical use. So this is how a modern, or I would say 10 years down the line, this is how things would look like when quantum things come into picture here. Okay, so probably as my time is short, I at least describe one problem, one of the problem that is called a radar com problem. Okay, so let's see. A quantum assisted framework designed for communication symbol detection in radar com, and probably another 5 minutes I explain the. So basically here I will not explain the details of the math, rather I'll show you where you can do the quantum there. So what part of the problem that triggers the quantum. Okay, so this is a typical system diagram which is a radar communication. So basically you have a transmitter here where I want to transmit a data, and there is a receiver here, but there is a radar here also. Okay, so which are operating at the same band. And this is a very practical example in 5G. You have a V2X or V2V where vehicle do anything, or a radar also come into picture there. So sometimes people call it ISAC, integrated sensor and communications. Sometimes people call it radar. So where radar is also there, communication is there. So what does the radar do? Radar will detect if there is any collision is happening. Suppose you are driving a car and on the highway, and you want to you want to do a kind of a collision avoidance. So there is a radar has to be there. Okay, and then once the radar gets the data, then it will transmit to the receiver and say, hey, this is what exactly it does. So radar takes the data, then receiver it can transmit to the receiver, or there might be another transmitter which also communicates to the receiver, but in the same band. So this is a very tactical example. It's used nowadays very much. Okay, so don't get into all this. Yeah. Okay, so I'll just try to try to trim the problem and try to see where I can show you the. So probably I will show you some of the issues. Yeah, just a second. Okay, so because as the time is less, so I will not describe too much on the on that front. So just trying to show you where exactly I can apply that. Okay, so let's see that. So I'm just trying to see relevant part where I can apply, because it's a very long presentation. I don't want you to go through everything. Only the relevant part I wanted to show you. Okay, so it is buried in the mathematics. I will explain in a simple mathematical term. Okay, so I will go to here. I'll again come back here. So where exactly your quantum can be applied here? So you have a TX, you have an RX, you have a radar. Okay, so it is there in the presentation, but it is it is buried in math. So I'll make it simplified. Okay, so now I have two receiver. One receiver is a communication receiver, another one is called a radar receiver. Okay, so what does the radar do? It sends a signal. There is an object and it sends it back, right? But at the same time, the transmitter also sends a signal which is meant for the receiver, but as it is operating at the same band, so it will create an interference. So this is a typical problem. So okay, so what it does, so the problem of the radar is that it has multiple antennas. Okay, so the job is to find out how many such objects are there. Okay, so what is the classical problem I'm solving? So what it does, you have multiple such antenna and you get the data y1 to yn. Let's say I have n number of data. So what you can do is that you can take it as a vector. So this is a classical way of doing it. And then you find out the covariance matrix of it. What is the covariance matrix? Expected value of y vector into y vector star. Okay, so this is a classical problem. This can be so this covariance matrix is a Hermitian matrix. Then how do I do a data detection? So basically, if it's covariance matrix, which is a Hermitian matrix, so what I need to do in classically I need to do eigenvalue decomposition, EVD. Now, moment I see it's a Hermitian matrix, I'm done. I mean, I'm blessed because quantum can handle Hermitian matrix. So what you do is that there is a standard process. So you take a Hermitian matrix. Then there is a method called QHS. So it is there in the presentation, but it is too detailed in mathematics. So I just make it simple. Okay, otherwise it will be of no use. So it is called quantum Hamiltonian simulation. So I'm not again going into too details of it. Is Hamiltonian simulation. So what it does is that it's a time simulation, meaning it takes the H in quantum machine and converts this matrix to U matrix, in real matrix, such that H minus U, their 2 norm is very, very close to 0. Okay, so that's the job of the Hamiltonian. So it does a Hamiltonian simulation and converts that U matrix. So moment it is a U matrix, I can implement it using Pauli gate. So I convert that to a U matrix, but I'm not done. Then what I do is I got U matrix. Then the process is that I have to do what? I have to do eigenvalue, because that is what the radar does. So how do I know how many objects are there? So what is the system matrix for a radar? System matrix for a radar is that if I have one object here, two objects here, three objects here, right? So radar sends the data here, 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 and it sends everywhere, and then it comes back, right? So as many as objects are there, that many number of, so it has to detect how many such objects are there. So what it does is that it basically takes the R matrix, which is a covariance matrix. So if there are three objects, then this particular R will have exactly three non-zero eigenvalues. Rest of the eigenvalues will be zeros. Okay, so it's a very standard classical problem. So the job is to find out the eigenvalue decomposition. But you see that moment I see there is a Hermitian matrix, I am jumping into for quantum. So this EVD estimation is not a simple thing. It takes almost O(n) cube complexity in normal classical. I mean, I can challenge. Suppose it's a 100 antennas are there. So what is the length of the covariance matrix? 100 got 100 matrix. 100 cross 100 matrix. You cannot do eigenvalue decomposition so easily in classical machines. You need, I mean, more than 5, more than 6 is very difficult to get it. Very, very difficult to get it. Impossible practically. Okay. So, but in quantum, it doesn't matter. Why? because I'll show you my simulations results that it doesn't matter if I have 1,000 antenna also, its complexity is nothing. So now eigenvalue decomposition, normal case it is O(n) cube. Now if n is 100, you think what is the complexity? 100 to the power 3. It's damn. I mean, you can't do anything with that. Okay, you can't do eigenvalues in a normal machines. Forget about your mobile computer or anything like that. But if it is in quantum, it's very easy. Okay, because why? Because what I do is that this H I run it. So this can be 100 cross 100 matrix, and quantum Hamiltonian simulation it can handle it. Then it will also be 100 cross 100 unitary matrix. Then what I do, I go through a process called quantum phase estimation. Okay, so it's a classical process. So quantum phase estimations is nothing but eigenvalue decomposition. Okay, and this overall complexity will be O log of n. Log of n I should not say, it's a poly of log of n. Now you see the complexity O(n) cube. But if I apply this quantum operation to find out the eigenvalue, it just takes polynomial of log of n. So now you can think how much the reduction in the computational things. So even if it is 100, it doesn't matter. It's a polynomial of log of n, right? Log of n meaning log of 100. What is that 100? If it is base 10, nothing, just 10, order 10s instead of 100 to the power 3. So that's where the advantage of quantum comes. So this is a very standard process. So the all depends on what exactly you want. If you have a Hermitian matrix, now you want to do a eigenvalue decomposition, this is the process. And this is the traditionally most of the times, this is what the route is. So in your problem, this Radcom problem, basically what we are trying to see here, show is here, we are trying to find out some sort of a Hermitian matrix problem. So Hermitian matrix meaning once I get the Hermitian matrix, I can do everything. But where I can get the Hermitian matrix? Okay. Another example I tell you, detection part, which again it is there, but it is buried in the mathematics. So I make it simpler. Okay. So let's say the same problem. You have the TX, you have the radar, and you have the RX. Okay. Same problem. So let's say radar is going to detect some objects here, and that objects will come here. So we have already done the object detection using the quantum. So what I did, I just took the covariance matrix, which is Hermitian, then I can do everything on the quantum. Let's do the same thing here on the RX side here. So what the RX will do here is that it also takes a signal Y is equal to, if I have a channel matrix X bar plus W. So this is the system equation. If I send a vector, okay, so this H is a matrix. Now the problem is that what is the what is the, how do I detect the X there? So I can detect the X using I can say H pseudo inverse into Y. It's a pseudo inverse, okay? So which means it's H star all invert into H. So that's the, okay. So this is multiplied with Y. Now this is a classical way of doing it, but H is not a Hermitian matrix in this case. So can I not apply any quantum here? Traditionally, no, but now I can see suddenly an interesting part. This, when I say pseudo matrix equation is this, okay? And as I said, when you apply a quantum to your problem, you have to see in your system or whatever you want to do, is there a Hermitian matrix? That's all. That is the only thing you have to find out. Then I see that, well, I have to multiply the Y here because this same thing is this guy, pseudo matrix. I say, yes, there is a Hermitian matrix. What is the Hermitian matrix? This is Hermitian matrix. This particular is a Hermitian matrix. Any matrix multiplied by Hx is a Hermitian matrix. Your H need not be Hermitian. It can be any matrix. But any matrix multiplied with its conjugate is a Hermitian matrix. Then I'm done. So that means what I'm doing is here is that a Hermitian matrix inversion. So at least this part, this inversion part, which is again a very complicated problem. For example, if this H is a 100 cross 100 matrix, can you do an inversion? I think I do not know how to do that in a classical, and it will never be working. Nobody has done. Okay, because it's not possible to do 100 cross 100 matrix inversion. But if this H star is a Hermitian matrix, I can do inversion very easily in the quantum. So what I need to do is that I can just define this matrix, let's say H into H star. What I need to do, I have to take the inversion of this guy, right? Okay, this again a very simple task. Why? Because there is a relationship between the inversion of this matrix and its eigenvalues. Okay, it's again a simple thing. For example, if B is a matrix, its eigenvalues are lambda 1 to, let's say, lambda 100. B inverse, what is the eigenvalues? All are invert, right? That we all know, right? So that means to find out the V invert, what I need to do is that somehow I need to find out this lambda and then I need to invert them. But at the same time, I have to ensure that this B is also multiplied with some unitary matrix because it's eigenvalue decomposition, right? So B can be, if it is a eigenvalue decomposable, then I can always write B is equal to U sigma into U star, right? Now, if it is a Hermitian matrix, I can always write like that. Any Hermitian matrix can be broken like that because every Hermitian matrix is a normal matrix and any normal matrix can be broken. So its EVD always exists. Okay, so these are eigenvalues. Now you see, now what is B inverse now? Very simple, U star sigma inverse U. Now how do I find out a sigma inverse? If I find out the lambda, I'm done. Because 1 by lambda calculation, which is very dumb. So if B is a Hermitian matrix, the only thing I need to do is to find out the eigenvalues. Then just invert the eigenvalues and multiply with its eigenvector. Now you can always question, how do I find the eigenvector? That's very damn easy in quantum. In fact, you don't have to even find the eigenvectors also there. You can just start with any unitary vector, you can get something there. That's not a big deal. So finding out this guy is the crucial part, but it is only possible if it is a Hermitian matrix. What is the process? Again, I use the same process, whatever it was. What I do here, I take that B matrix, okay, then I do QHS, quantum Hamiltonian simulations. I get a U. What I do, then I have to estimate the eigenvalues, right? So that's the technique called QPE, quantum phase estimation. You get all the eigenvalues, so just 1 by lambda, you create it 1 by 1, 1 by lambda 100, whatever. So that's it, I'm done. So if I get eigenvalues and just invert it, then I can get the B inverse, because what I need to do is U and this matrices having these quantities, which is sigma B inverse and U star. So this is what my inversion. So you see where is the complexity involved? Nowhere except this QP, which is very simple job. QP is a quantum phase estimation. So that can be done in one single operation. Okay, so hardly any computational complexity. I don't have to do any. So if had I tried this whole thing in a classical, I had to do Gauss elimination. So which is O, whose complexity itself is O and Q. And what is its complexity? It is O of log, sorry, not log exactly. It is the polynomial of log of n. Look at the level of reduction. It's nothing. And that's why you can see some results here. So I will directly go to the results section. I'll show you how much reduction you may get it. This is one of the results. Okay, so you can see some of the results here. Yeah, this can be one of the results here. So this is you can see hardly any 1,000, and this become 4,000. So that's the kind of reduction you get in the complexity. Okay, there are some more results I may have it. Yeah, this is the one. Yeah, this is also another results, but I think it's for the radar part. You can see complexity is hardly anything here. So after, as I increase my dimension, complexity is almost flat, but otherwise it is very, very big. So that is precisely where my things come into picture. Okay, and some of the errors, you may think that, hey, quantum is also giving some error, right? Because that is also quantum machine. Quantum machine has errors compared to normal machines. Normally the CMOS machine, which are very steady, but quantum machines are not exactly CMOS. Okay, so that's a different material. So it has a lot of thermal noise. So that creates still an issue, so that it adds noise. But we see that it doesn't create too much deviation. For example, this is another curve where you can see that dots are normally VT, and these blocks are basically the one which is quantum. So almost no error. Hardly you can see some errors, very little bit, but there is almost no error. So I can say the eigenvalues which I estimate are almost matching with the classical ones. Yeah, so that's it. So I think to summarize, what I can say is that you need to find out a system matrix which is Hermitian. So if I want to summarize it, let me summarize it. So your system matrix. Now system matrix need not be the, let's say, y is equal to h of x. That's a system matrix. This need not be Hermitian. Okay, if it is Hermitian, I can directly do a eigenvalue decomposition and find out the inversion of this matrix. That is okay. So if that is the case, okay. But sometimes the operational matrix, for example, from here, if it is a radar equation, so there will be multiple such antenna. Let's say it is n antenna, so this will be an n plus 1 vector. So if something like that comes into picture, but I don't want to take that one directly, but rather I want to take expectation value of I y vector star. Now this becomes Hermitian because that's the covariance matrix. So something like that. So you have to have a Hawk's eye. So I always say Hawk's H-A-W-K Hawk's eye. Okay. Moment you have a Hawk's eye, you find out in your operation who is the guy having a Hermitian property. So any matrix which has a Hermitian property, just target that and see what you can do with that Hermitian matrix. Eigenvalue estimation, SVD estimation, or you want to do inversion. These are the basic three properties usually we all use it in any communication systems of signal version. Either communication, meaning either inversion, EVD or SVD. These are three main operations we do. So if it is a Hermitian matrix, this just two steps you need to do. One step is what is that? I think I removed it. One that convert that matrix to unitary. So step one, H should be converted to U matrix. Step two, on U you apply quantum phase estimation and get eigenvalues. Because in quantum everything is eigen. Because if it is a Hermitian matrix, you want to do inversion, you need an eigenvalue. Okay, you want to do a singular value decomposition, you do an eigenvalue. You want to do an addition, you do an eigenvalue. So everything is eigenvalue. So these are the two steps you need to do. Hermitian to U using quantum Hamiltonian simulation. And from U, once you get it, you apply a quantum phase estimation, you get the eigenvalue. So once you get it, you are done. Your problem is solved. So you can do inversion, you can do EVD, you can do SVD, whatever. Everything is from that, and all can be done with quantum. And what's the complexity? Is logarithmic scale, log of polynomial of log n. Yeah, so that's precisely what it means here. Okay, so I'm done on that. So I did not go to the complete presentation, which is fine because that's more rigorous and mathematical. So I just explained in a very simple way what quantum is and quantum communication is. Okay, folks, I'm done. If you have questions, let me know.
Thank you, sir. Thank you for your informative session on quantum communication. So there is a question arises from Dr. Arindam Sadhu. He raises his hands. Dr. Sadhu, you can ask any question you want to ask. Please go
Am I
on.
audible? Am I audible,
Yes,
sir?
yes, you are audible.
Thank you very much, sir, for your nice presentation over here. But lots of query are there regarding the quantum communication. Today is clear to me. Now, I have two questions regarding that one. That whenever you are saying that we are converting from the classical to the quantum bit, as we know that one, all the inputs are basically analog. So first of all, we have to convert from analog to digital, then from digital bit to quantum bit,
No, it is
or
basically all
it will be
around.
the.
So yeah, so I'll tell you what it means. Sorry. So let's say you have an antenna here. Okay. So
Yes,
that's
sir.
let's say you receive RT. Then you do a demodulation. So that's okay. Demodulation, blah blah blah, and finally you have to do ADC, right? ADC sample. So when it is ADC sample, it's like samples, right? So ADC may be 8-bit, so it's a fixed pointed ADC sample, it may be 8-bit sample. Now I'm talking of this whole value. So notionally it is digital, but actually the value is like it's a value, it's a real-time value, but inherently it is a digital, so it's an 8-bit digital. Okay, but so when you go to the quantum, this 8-bit digital, which is also some inherently representing a decimal, right?
Yes.
So this 8-bit will come here. Got it? 8-bit will come here into the quantum machine. And then it will be converted to its. So basically what the quantum machine will take it has an interface. So it takes these 8-bit values, inherently convert to exactly not a decimal, but a format which it understands. So to answer your question, you are not giving RT. I think that is what your conclusion. So RT you are not giving to the quantum machine. You are giving these ADC samples, which may be 8-bit, 12-bit, or 16. So each sample is a 12. So you are parallelly giving 8-bit all together. So internal notion is that it has a decimal value, and that value will be reconverted back to some quantum values. That's all. Okay. So you don't give RT, rather you give the ADC values.
ADC
Am I
values.
making sense?
Okay.
Yeah.
Yes, sir. And another part
But
is basically part from.
my point is that don't get confused with this digital value and quantum machine's digital values. Okay, so when I write 0, 1, it is not the 0, 1 notion here. 0 is just a notion.
Yes,
It is a function. It is a
exactly.
function which is orthogonal. Yeah, it's just an orthogonal notion, not the value digit 0, not the value 1. That's all.
We have to represent in matrix form. That is, for 0 is 1 0, and for 1 is 0 1.
You can do that way. You can do that way too. So it is digital that
Another
goes
part,
there, but in parallel. Yeah, please go ahead.
for the part of the quantum crypto, basically we are doing some computation part. As we know that whenever we are cascading our Hadamard gates over here, we'll get the RNG or quantum RNG number, and they are getting the same probability of, if I'm taking the 3-bit quantum bit. So my question is that sometimes whenever I'm doing the computation, output of a reversible gate is coming that their output probability is also different. So actually, I'm confused about the how I do the NISQ test for that data whenever the probability output of my probability is different.
Yeah, so you want to get, So what I understand correctly, so you have a quantum bits 0, 1, 0, which is not the,
Yes.
but this is just a vector. This is not 0, 1, 0, right? So this is just a stage. So you can inherently encode classically as a 0, 1, 0. That is your choice.
Yes.
So you can also classically encode it as a 1, 0, 1 also. Okay, that means 0, 1, 0 in a quantum, which is, so 0, 1, 0 is just a namesake. There's no other value. So I could have written a also. Let's say a1 plus a2, like that. So internally I say a1 meaning 101, a2 meaning 0, 1, 100. That's my digital conversion. Quantum doesn't understand what is 101, 100. So now the question is that, let's say here is my point. I think I got your point. What you want to say is that, let's say I have an output psi, which is, let's say this is alpha 1 plus alpha 2. Okay. Now this is what the quantum gives me. Inherently, I know a1 meaning 100, a2 meaning 010. That is my own classical mapping. But I have to get a1. Suppose I want to get a1 more and more. So I need to, I need to increase this probability. So basically what happens for any quantum, so this is xi. There is another block which I have not mentioned. It's called a measurement block. Okay, so what does the measurement block do? So it's an orthogonal basis measurement. So what it does is that it has a measurement on basis A1. It has a measurement on basis A2. Okay, so it gets a xi and try to project on A1, try to project on A2. So when I measure it, in fact, I will get A1, I will get A2. Either I can get A1 or I can get A2. Both. So you can't say that I will always get A1 or I will get A2. No, nothing can be done. I can either get A1 or I can get A2 because this xi contains A1 and A2 both. So now it's a problem, right? Because you are getting A1 and A2 both. So which one to pick up, right? So what happens is that you do not do one measurement. You do many measurement. N times measurement. Okay. Then you try to see out of this n measurement who comes larger most of the time. Suppose this alpha 1 is greater than alpha 2. Out of the n, most of the time a1 appears. Then I said, okay, probably I want a1 more. Now say that, okay, you are not satisfied with a1 because you say that my a1 is actually not what I want to know, though I have done multiple such measurement. So it will give you probabilistically out of the n measurement. If alpha 1 is more, let's say alpha 1 is 0.6 and this is 0.4. Okay. So 60% time A1 comes, 40% time A2 comes, as simple as that. Okay. But what if you do not want A1? So it is you who has to ensure that alpha 1 has to be increased. So how do I do? Again, it's an operation. So what you do is that you take the xi, pass it through some other Hermitian block or some operator. It could be Hermitian or it could be some U operation. Then you get another xi1. But you have to design this U1 tactfully such that your alpha 2 increases. So that is up to you. How do you want to do that? So there are many ways to do that. Okay. So now you do a measurement and you get most of the time A2. So this is how it is done. So you cannot trust the quantum output by only one measurement. You have to do multiple measurement and take an average out of it.
Okay.
Okay,
Thank
thank
you.
you.
Thank you.
Thank you, Professor Amit Kumar Datta, sir, for your nice, informative talk in your auto FDP program. Sir, we have a small token of greeting for you from our college, Dr. Subir Chandra Engineering College and Sports Complex. Please, sir, accept it, and
Thank you.
and we will send you in your email ID later. And thank you, sir. Thank you for your informative session on quantum communication. And
Yeah.
I hope all are listening carefully, and they will be flourished from this information. Thank you, sir. With permission of
Thank
you, we will proceed for the next session.
Sure.
Uh,
Thank you.
Thank you, sir.
Thank you. So I leave off.
Yes, sir. Okay.